Hi, this is Bill from DX Connection K38ZP. I'm going to discuss electronic bias systems for grounded grid amplifiers. Today I'd like to talk about the requirements of an electronic bias system, the advantages of an electronic bias system, and also we'll go into the block diagram of a biasing network here. First, why would we want to use an electronic bias system? Well, what it does is when you're not talking or there's pauses in the speech, it reduces the idling current in the amplifier. And then when the speech comes on, it immediately switches to the normal biasing level and then remains there for short periods after your speech. This causes your amplifier to run cooler, puts less stress on your power supply, keeps your tubes a little cooler, and in general it's just a way of preserving your amplifier. First of all, what does exactly does the electronic bias system try to do? Well, what happens is when you're normally at very low levels, your amplifier will draw a very slight amount of current. Like for instance on a SB220, the idling current, rather than being 0, might be like 7 milliamps as opposed to the normal idling current over 100 milliamps. So if you calculate the power dissipation at 7 milliamps versus 100 milliamps, you get well over about 9 times reduction in idling power. So that causes everything to run cooler. The electronic switch, then we'll talk about what amount of idling current you need. In other words, what level of signal will the amplifier pass in class A, and then what level the bias should be switched to the normal AB level. And when it switches from the class A level, which is very low, like at the 7 milliamps level, it has to switch quite rapidly so that it doesn't distort the switch. Rapidly is typically around 50 to 100 microseconds, maybe a little bit longer. For speech, 3 kilohertz speech, you really don't have a real high rise time that you have to meet. So you do, though, have to meet something in the order of 100-150 microseconds rise time there. So with that, we'll go on and talk about the block diagram of a electronic bias system and how it fits into the normal bias network. We're going to look at a normal bias system from an SB220 type amplifier. Any other grounded grid is very similar. These is basically for 3 500Z tubes. We see the grid here is grounded. In this case we show it directly. Sometimes it's through an RF choke or capacitor. And then the normal feed system from our input matching network goes to the cathode, which is also the filament. The RFC or RF choke preventing RF down here. Here's the filament fed by a 5-volt AC transformer that's center tap. Now this center tap is where the bias voltage is introduced. I show the amplifier transmit receive relay in the transmit position coming down through a Zener diode, which is the normal way they generate the bias voltage, and there's also in a SB220 a 0.82 ohm resistor for metering. So this is the voltage that we have to replace, that when instead of keeping it always at 5.1 volts when there's no audio coming in, we want to raise that voltage up to some higher value, and the higher value will depend on what value we need to achieve our class A milliamps or current requirement. So anyway, our whole discussion is going to be just to replace this one diode, Zener diode here, and we'll show how we have to sense the input coming in, which in this case will be right here from the matching network, is where we're going to pick off and sense when there's RF present, and then we're going to put a circuit in here to replace this 5-volt Zener so that the voltage will only be 5.1 volt when there's an input. When there's no input, it will go up to higher voltage and reduce the current through the amplifier. So it really is not a very complicated problem. At least it doesn't look that way at first. So let's get into it. Now we have a grounded grid biasing system here now with the electronic bias system block here. Down here is the electronic bias system that we've added to replace the Zener diode on the previous schematic or block diagram. You can see it's very little different, except the input here, this input matching, again, goes up to where the input matching network connects to the tube there. And this is where it's going to sense the RF, and this is how it's going to control the bias here. It looks pretty simple there. There's not a whole lot to do. You just have to connect up this sensing network to the tube. You don't remove any wires, just tap into there and hook onto ground. This you have to disable the other Zener diode or remove it out of the circuit. It's easier just to disable it by shorting across it. And then we'll show where we can open the, take one wire off, put the existing Zener wire, go into here, and then we'll have to add a little jumper wire from this output to the previous wire that was there. So that's it. This is the only circuit that has to be unsoldered and a little wire replaced. This just has to tap into it. So the nice part about the electronic bias system, it really doesn't require a major change to your amplifier. And really, to go back to the original design, you can just take off the voltages, or take off the wires that were attached here, enable the Zener diode. What I do is I just put a short wire across this, or remove the short across the Zener and connect these wires together again with the Zener down here, of course. So there we go. Now let's see what this can do for you there. We'll start working towards what this looks like in a real amplifier now. Okay, now here's the electronic bias system circuit here in the HL2200 Heathkit amplifier. It's the equivalent of the SB220 Heathkit amplifier in the area we're talking about as far as electronic bias. Here's the circuit. The RF input and ground are right here. So here's the RF input going over to where that matching network comes into the tube. There's the two capacitors that are feeding the cathode or filament. And here, this black wire here was originally right here where this red wire is on this relay here on the lower contact down there. And so I had to take off this wire and add a wire from the circuit here, which is the plus part on the previous diagram, over to here. So that was the wire I had to add. This wire I had to extend, the existing wire I had to extend down here to the minus part of this circuit. This transistor here controls the bias voltage. So the voltage is settable. You can't see it, but there's a little trimmer pot here. Allows you to set what the voltage you want to use. Anywhere between about little less than 4 volts up to about 10 volts. It's good to try to put this pass transistor here in some type of airflow. In this amplifier, there's quite a bit of air comes from the fan here across the pins and here, so it gets a fair amount of cooling there. But with this particular amplifier, it's only a 5-volt bias and a amp maximum current, so it does not get that hot, so it's not a real big problem. And the lower the bias voltage, typically the lower the dissipation in this pass transistor, because most amps, and I'll just have to typify that, most typically don't draw over an amp or a little over an amp of current. So the bias voltage tends to be more dissipation the higher the bias voltage you require. Something like an AL811, which only requires about 4.2 volts, would have less dissipation, even though it can draw up to an amp, I believe. And some that use 10-volt bias, now you have to be a little more careful with airflow because you don't want to overheat this. Other than that, that's the only other thing I've done is I've built a little bracket here to support it. There was an existing a screw down here that I loosened, slid the bracket under, and only have one screw holding this. It's more than enough. This is very light, and there is another hole available here if you wanted to put another standoff. This is at ground potential, and these are ground potentials. However, this is at the bias potential, so you don't want this unless you insulate the transistor, which it's not now. You don't want it to touch ground or anything else. And that's it. That's electronic bias system as applied to an SB or HL2200. We'll show you a little bit how it works here in the next part of the video. There is one other thing I would like to point out about setting up the bias. Remember, I said that we need to have some minimum current. In this particular amplifier, we chose 7 milliamps, and we'll discuss later why that was a good number for this particular combination. How we set that current, though, is this transistor, or I'm sorry, this resistor here. I have a pair of 4.7 ohm, 4.7 k ohm resistors in parallel, which gives me a little over 2.35 k ohms. This is what sets the current when the circuit is not active. So when I turn it on and I go into transmit, these resistors control the current. I can't even see the current on a meter, although I've measured it with more sensitive meters, and it's set up to draw 7 milliamps. So this is the other thing that may or may not need to be set. It depends how particular you are on what the minimum current is. It's not a big deal. When you're getting down 5, 7, 10 mils, I can't get excited, but typically around 2 to 3 K seems to work good. And if you do the calculation, you don't really need a lot of high power resistor. I made this, I believe, a 1/2 watt. The voltage, when it's not turned on, only goes up to 16 volts with this resistor combination. So if you calculate 16 volts squared over 2.35 K, you'll see what the dissipation is of this. It's not as great as one might think, but you know, 1/2 watt resistor if you want to be conservative. But anyway, that's how you set the idling current, which we'll talk about later, how that comes into detecting the threshold of the circuit, or relating it to the threshold of the RF circuit here. And I don't know, you probably still can't see the pot back here. I was hoping you could, but okay, as I'm assembling the amplifier here, I wanted to point out on this particular amplifier, an SB220s, that the Zener diode is right under here. Right under this. If I took this lid off, you can see it. It's right at the top of the board, so it's very easy to get to. And like I said, I just put a soldered a shorter wire across it there. So I just wanted to point out where you need to look for that Zener diode that we're bypassing. Okay, now we have the amplifier turned on here. It's in idle mode, and notice when we key it up, there's just a little blurb at the beginning, but the current is really low. I don't know, I can't see it, but it's not there. Now we're gonna, so we let go, there's a little blurb, and then I have my QSK 2500 box in there, so there's a 3-second delay when I let go of the PTT. But it's kind of unnerving at first to look at your plate meter when it's keyed up and see basically no current. Okay, now we're gonna put a little RF to it. Now this is basically as low as I can go. It's putting out, it's, you know, maybe a little over 100 watts right now. No, that's 250. Yeah, it's around 100 watts, but I'm driving it with my ICOM 735, and without using an attenuator, that's as low as I can go. But that's basically still just idling current here. That's the normal idling current that it is when I'm keyed like this. Hello, now we will describe what an electronic bias circuit should do in normal operation and what the requirements are in each amplifier. An electronic bias circuit will normally switch between the amplifier in low power Class A mode to higher power Class AB mode, and the way it does it, it changes the bias voltage for the amplifier. When there's no RF input, the amplifier should operate in low power Class A mode. This reduces any distortion on the weak signals going into the amplifier. When the electronic bias circuit senses the RF power input to the amplifier, it will then change the amplifier from a Class A mode to a Class AB mode. So the Class AB mode is the normal operation of amplifier, and this is a lower bias than in Class A mode. And the reason for doing that is to be able to accomplish or produce the output power that you have to with large inputs. So we have to select the way the electronic bias circuit does this selection is it measures the RF input to the amplifier. And when the power input gets above a certain threshold that the Class A amplifier will no longer produce without distortion, it switches the bias to go into the Class AB mode, which means the amplifier will draw more current and be able to handle the stronger signal with minimum distortion. In reality, though, the electronic bias system must go back and forth between the two modes of Class A and Class B by adjusting the bias level. It uses a fast attack, sort of like automatic gain control, or AGC, and a slow delay constant, time constant that is. Okay, now we need a criteria for switching between Class A and Class AB. Now we want to be we want to switch out of Class A into Class AB before we get distortion, and vice versa. When the signal level drops below a threshold, we want to switch back to Class A to minimize power dissipation. This is typically after 50 to 100 milliseconds of input below our detection threshold. Now, how do we set our Class A power? We want the Class A power to be as low as reasonable, but not too low, because if it's too low, the amplifier might switch into Class AB at very low audio levels, such as background noise, fan amplifier noise, etc. So if you make it too sensitive, the electronic bias system may never get out of Class AB mode and really defeat the purpose of it. So we want to pick a Class A level that is reasonably low but doesn't cause the circuit to trigger into Class AB mode with a very, very low background noise. Now, experimentally, we found that a Class A idle power of about 20 watts is reasonable. Since Class A efficiency is 50% maximum, the maximum output power in Class A is only 10 watts. So we have to make sure that we don't exceed 10 watts before we switch into the Class AB mode. Well, how do we determine what the threshold should be for our detection sensitivity of our electronic bias system, which is looking at the RF input to the amplifier? The power gain of an SB220 is about 11 dB. At this gain, the 10 watts output corresponds to 0.79 watts input to the amplifier. If the input impedance is assumed to be 50 ohms, the input voltage is 6.3 volts RMS, or about 17.8 volts peak to peak. It's easy to talk about peak to peak voltage because the input impedance of the electronic bias circuit is quite high, and it does not load or have an effect on the input impedance of the amplifier. The RF detection sensitivity of a EBS 2500 circuit is about 4 volts peak to peak. This is kind of typical of most circuits out there. The RF sensitivity guarantees that it will switch to AB mode before the RF voltage reaches the 17.8 volts peak-to-peak max, which is, we definitely don't want to exceed it, but we can go into class AB before this. My background noise does not trigger the electronic bias system out of AB, so this allows enough AB power that I can have the sensitivity not too high so that I go into AB all the time, and I do go back to class A, which is what we want to do to minimize power dissipation. Well, in conclusion, the point of this discussion is a way to describe how much power dissipation you should have before the electronic bias system kicks in. It also says that we need to have a minimum amount of Class A power dissipation and not cut the amplifier completely off with the electronic bias system. With more background noise, it says that we really need to raise the amplifier's Class A dissipation and decrease the electronic bias system's detection sensitivity. Otherwise, even though we're dissipating a little bit of power in the amplifier, we're still not going into class AB all the time. On the other hand, if we want to get maximum reduction in dissipation, we can lower the electronic bias system sensitivity and thereby lower the power dissipation we require in class A mode. Now, the way this class A mode dissipation is controlled is quite simple. As shown in some of the other diagrams, there was shown a resistor that is put in there. This resistor is actually across the plus and minus terminals of the electronic bias system, and it just causes the amplifier to draw a little current. So it's very easy to control how much power you want in class A with a simple resistor on the electronic bias system, or you can put the resistor externally across the terminals of the electronic bias system. With this example, though, the Class A idle power could have been reduced by at least a factor of 4 down to 5 watts. This still allows the EBS sensitivity to go into Class AB mode before we reach the distortion point. The RF power should not be put too low because we need some conservative protection that the sensitivity is not going to be the same in all installations, and it may vary depending on the actual impedance at the of the tube input there. So I recommend that the Class A power be able to handle 2 to 4 times the calculated power that we showed that with a Class A amplifier, and this is based upon 2 to 4 times the minimum sensitivity or lowest sensitivity of the EBS detection sensitivity. Hope this is not too confusing. Allows you a rational way to set the idling current with the EBS circuit not triggered, and give you a criteria if you have a problem with background noise, how to adjust your sensitivity, and how much Class A power to dissipate. You can vary the sensitivity simply by putting a resistor in series with the RF input to the EBS circuit. Thank you, and good luck.